Well, today we're going to look at a different way to represent the plane. Up to this point in your mathematical childhood, you have only talked about Cartesian coordinates and the Cartesian coordinate system, where you had a set of ordered pairs x comma y. The problem with that is there are lots of equations that they don't easily represent, as well as when you start doing calculus on things, sometimes you like to look at it from a little different viewpoint. And that different viewpoint today, at least, is polar coordinates. All right, so polar coordinates are ordered pairs as well, but their ordered pairs are r and theta. Now, your author writes polar coordinates with round parentheses. And he also writes Cartesian coordinates with round parentheses. I don't like that. So whenever I write round parentheses, or whenever you write round parentheses for me, you mean Cartesian coordinates. Polar coordinates, I will always use square bracket notation. That's common in lots of books. Not common in yours, but that's the convention we're going to hold. All right, so what is r and theta? Well, so I have a point in the Cartesian plane represented by an ordered pair xy. All right, if I draw a ray from the pole out to that point, that defines a side. If I drop a perpendicular down to the positive arm of the x-axis, I get this little triangle where, at least if I'm in the first quadrant, this length is x, this length is y. What is theta? Well, theta is any angle that starts with the positive arm of the x-axis and ends, that is, has terminal side, on that ray. There's one theta I've drawn. Obviously, I could take that angle and I could go 2 pi and then back up. That would be another angle that would do the same thing. All right, so what's theta? Theta is the angle made by the positive arm of the x-axis, the initial side, and it ends, after some time perhaps, on the ray that comes from the origin to the point. What's r? Well, the absolute value of r is the distance the point is away from the origin. Well, if I look at that, I've got my little old Pythagorean theorem floating around. So the absolute value of r actually is the square root of x squared plus y squared, and I'll talk about that in a second. All right, so theta is this angle. Now, if theta is measured counterclockwise, then it's considered to be positive. So counterclockwise would be this way. Now, if it's measured clockwise, then we take theta to be negative. So if I start here and go down this way, I'm going in the negative theta direction. And if r is greater than 0, it's like the picture I have here. But if r is less than 0, then I have to reflect it through the origin. That's what a minus r means. All right, so some remarks with respect to polar points. The first remark is that polar points are not unique. That is, I could have two different points or two ordered pairs that represent the same point. Okay, and that's because the angle theta need not be unique. All right, so if I want to do some conversions from Cartesian to polar, here are the conversion equations I use. The absolute value of r is just this distance, which is, by the Pythagorean theorem, the square root of x squared plus y squared. Tangent of theta, I don't care where you happen to be, tangent of theta always turns out to be y divided by x, even if you're in the second, third, or fourth quadrant. Okay, if I draw this little picture here, you should see that x can always be represented as r cosine theta and y represented as r sine theta. It's clear here if r happens to be positive and that's theta, okay, then sine theta is what? Y over r, which would make r equal sine theta, or y equals sine theta. X over r is cosine theta, which would make x equal r cosine theta, right? So these are the conversion equations that one uses. The top two convert from Cartesian to polar, and the bottom two, if I start in polar, I know what r and theta is. I can find x or I can find y. All right, so let's look at a particular example. How do we represent 2 comma 2? That's Cartesian, remember, round parentheses Cartesian, in polar. Well, there's 2, 2. I draw this little line right here from there out. What's that distance? The square root of 4 add 4, the square root of 8, or 2 square roots of 2. So the absolute value of r is 2 square roots of 2. Okay, now what's the angle? Well, since that splits quadrant 1 in half, that angle is, of course, pi over 4. I could also find it by using this little equation here, right? 2 divided by 2 equals a tangent of theta, find theta. So here are the polar coordinates, r comma theta. One way to represent it is 2 root 2 pi over 4, okay? Theta is the angle pi over 4, r is 2 root 2. But you will notice that if I take 2 root 2 and take pi over 4 and add any multiple of 2 pi, I'm back to the same spot, right? So in other words, 2 pi add pi over 4 still puts me up there. 4 pi add pi over 4 still puts me up there, right? So here are infinitely many representations for the same point. Remember, I told you polar points are not unique, as in lots of ordered pairs represent the same point in the plane, and that can cause a little trouble sometime, all right? So here are a set of coterminal points, that is, they represent the same point, right, but are different polar pairs. Pi over 4 plus 2n pi, and you can add any multiple of 2 pi, or you can subtract any multiple of 2 pi. That's why I have n element in the integers. All right, what's the other representation for this point? Well, the other representation is if I were to take pi over 4 and add pi, that would put me down here. But if my radius were negative, I said anytime you have a negative radius, it gets reflected through the origin, and that would put me back at the same point. So let me say it again. Pi over 4, add pi, puts me exactly down here. If I represented negative radius, I'd be back over there. And so here are the other representations for the point 2 comma 2. R being minus 2 root 2. Remember, r can be positive or negative. So can theta. And then I have, what, pi over 4, add pi. But of course, if I go and add multiples of 2n pi to that, I land in the same spot. Okay, and now a way to represent that is to combine pi and 2n pi to give me 2n plus 1 pi, add pi by 4. So here are all the polar representations for the point 2 comma 2. Now, let's go back the other way. I have a polar point, and I want to represent it as a Cartesian point. Well, there's only one way to represent it as a Cartesian point. All right, so here's my polar point. What am I telling you? That r is 2 and theta is pi halves. By the way, if I say pi halves, that means I start the positive arm of the x-axis, I go 90 degrees, pi over 2, I'm up there. Radius 2, that puts me right up here. I can tell you I'm at the point 0 comma 2 in Cartesian. Get it? Distance away 2, angle pi halves, so it's 0 over 2. Now, what if life gets a little more complicated? Example 3, 4 comma 3 pi over 4, so 3 pi over 4 puts me in quadrant 2. This is a distance 4 away. I'm interested in what the Cartesian coordinates of that point are. Well, remember my conversion equations. X is r cosine theta, y is r sine theta. So x is r cosine theta, which is what? 4 cosine of 3 pi over 4. Cosine of 3 pi over 4 is minus root 2 over 2. I get minus 2 root 2. Y is r sine theta. That's 4 sine 3 pi over 4. But sine 3 pi over 4 is root 2 over 2. So y is 2 root 2. So the ordered pair is minus 2 root 2 comma 2 root 2 in Cartesian. All right, now I want to talk about converting not points, but equations from one type to the other. Suppose I want to take this Cartesian equation, x squared plus y squared equals 4, and convert it to polar. Well, I could do that lots of ways. One way is everywhere I see an x, I stick in r cosine theta. Everywhere I see a y, I stick in r sine theta. By the way, you should recognize x squared plus y squared equals 4 as being what? A circle centered at the origin of radius 2. Right? But, so now let's take this and plug these things in. I get 4 is x squared plus y squared, r squared plus cosine squared plus r squared times sine squared. Factor out an r squared. Cosine squared plus sine squared is 1. I get r squared. So r squared equals 4 is a way to represent this equation. Not surprising, right? By the way, r squared equals 4 is the same polar equation as either r equals 2 or r equals minus 2. Another thing I might say is if r is ever 0 in the polar equation, I don't care what the angle is, my friend, you are at the origin when r is 0. All right, now suppose I want to take this equation, r equals sine theta, and convert it to Cartesian. Well, the slick way to do it is this. R equals sine theta. I'm going to multiply both sides by something, r. Why? Because on this side I get r squared, and on this side I get r sine theta. Now, what were my conversion equations? I know what r squared is. It's x squared plus y squared. I know what r sine theta is. It's y. So I get x squared plus y squared equals y, and guess what? I've just converted a polar equation into a Cartesian equation. And I urge you to put that in standard form and realize that that is a circle. It's a circle, although its center is no longer at the origin. All right. Let's do the final example, example 6. Take x plus y equal 3, convert it to polar. X is r cosine theta, y is r sine theta. R cosine theta plus r sine theta is 3. If I were to factor out an r, I'd get this. If I were to solve for r, which lots of polar equations are solved for r, just like lots of polar equations are Cartesian equations, are solved for x, I would get r equals 3 divided by cosine theta plus sine theta, and that is my equivalent polar equation. Well, so that's an introduction to polar coordinates. Hope all is well. Bye.